Hello students, I am Azizi, Professor Electronics. In our previous session, we have learned that how to print the embedded data on LCD display and how to display a text message on LCD display. In this session, we will learn that how to increment the value of the counter with a delay of 1 second. And to increment the counter with a delay of 1 second, we will use the timer 0 interrupt of 889C51 microcontroller. So first we'll go through our previously written program, then we will write a new program to increment the value of the counter. So let's start our today's session. And here we can find our previously written program to display the embedded data on LCD display. And we have written our program for the microcontroller, that is 889C51. Now in this session, we'll increment the counter value with a delay of 1 second, and we will use the timer 0 interrupt to develop the delay of 1 second. First, we'll discuss that what is an interrupt, and then we will learn that how many interrupts are there in MCS 51 family. And here we can understand the concept of interrupt and polling. Our CPU, that is the microcontroller, is a mindless servant. The intelligence to the embedded systems comes from the brain of the programmer, and the CPU will only execute the program which is written by the programmer. Whenever the CPU or servant will wake up, it will go to a particular address. That is called the reset vector for the microcontroller and microprocessor. A microcontroller or microprocessor can have different addresses depending on the length of the address bus. If the address bus of the microcontroller or microprocessor based system is 16-bit, it means that it can read or write up to 64 K locations. Here we have only 16 addresses to understand the concept of interrupt and polling. If the CPU or the servant will wake up, it will go to the address that is 0 or the room number 0. And here at the address 0 or the room number 0, it will find a program or instruction. As we have written the instruction on the 00 address in our previous programs, that is jump to initialization routine. After executing this instruction, the servant will go to the room number 1, and here at room number 1, it will find some other instruction and program to execute. Similarly, after executing the program which is written in room number 1, the controller or the servant will go to the room number 2 and will execute the program or instruction which is written in room number 2. The servant will go to all the rooms one by one and will execute the program or instruction written on particular address. This is what we call polling. That is, after executing the program written on room number 0, it will go to the room number 1, then go to the room number 2, 3, 4, 5, 6 and up to the maximum address, that is 15. And after executing the instruction written on room number 15, it will again go to the room number 0. What could be the instructions for a computer hotel? That is to clean the room, change the bed sheet, deliver clothes to the laundry, bring clothes from the laundry, bring food from the kitchen, do nothing, go to room number 10, stay in room number 10, put my message to the mailbox and bring the message from the mailbox. But the microcontrollers and microprocessors have different instruction set. That is, move the data to a particular register, increment the data, decrement the data, compare the data, and set or reset a particular bit. But an interrupt could be a synchronous or asynchronous event, having a particular address to execute the interrupt service routine. Say for example, in our computer hotel, if the interrupt will come from the front desk, then the address of the front desk will be different, and the interrupt service routine for the front desk will be different. But if an interrupt will be generated from the washing machine bell, then the address of the washing machine bell is different and the interrupt service routine for the laundry is different. Similarly, interrupt could be generated from the kitchen, which has a particular address, or interrupt could be generated from the mailbox, that is, a new message is ready to receive or a new message is required to deliver to the outside client. Similarly, in the microcontroller, we can have different types of interrupts, and here we can find a particular circuit, that is power on reset circuit. That is a wake-up call for the microcontroller, and this wake-up call will force the microcontroller to jump to the reset vector address, that is 000H in case of MCS 51 family. And now we will learn that what are the interrupts of MCS 51 family. And here we can find different interrupt vector addresses for MCS 51 family. That is 000H for reset, 0003H for external 0, 000BH for timer 0, 0013H for external 1, 001BH for timer 1, 0023H for serial interrupt, and 002BH for timer 2 in case of 889C52 microcontroller. But in 89C51 microcontroller, we have two timers, that is timer 0 and timer 1, and their interrupt vector addresses are 000BH and 001BH. Whenever the microcontroller will receive a high pulse on reset input, that is pin number 9 of the microcontroller, it will jump to the address that is 000H and will execute the instruction which is written on the 000H. In our previously written programs, we have not used the addresses, that is 0003H, 000BH, 0013H, 001BH, 0023H and 002BH because these vector addresses are reserved for the interrupts. And to enable or disable these interrupts, we have to configure the different bits of the special function registers in the microcontroller. and we will learn that what are the bits to control these interrupts in the microcontroller. As we will use the timer 0 interrupt in our next program, so we will use interrupt vector address, that is 000BH, and we will also learn that what is a timer 0 interrupt, and here we can find a special function registers of MCS 51 family. That is the timer low 0 at the address 8AH and the timer low 1 at the address 8B. The timer high 0, the address is 8C. Timer high 1, the address is 8D. And here we can see another register, that is interrupt enable, at the address A8. And here we have a special function register, that is T mode, timer mode, at address of 89H. And here we can find another special function register, that is TCON, at the address of 88H. And now we'll learn that how to configure the bits of these special function registers to enable or disable an interrupt. As we will use the timer 0 interrupt in our program, so we'll use the register, that is timer low 0, timer low 1, and we'll also configure the bits of the timer mode register. We will also use the bits of the timer control registers in our program. 8089C timers or counters. Let's see for the microcontroller, that is 8089C51, what is the concept of timer 0 and counter 0. Timer 0 of the 8089C51 microcontroller is a 16-bit register which is divided into two 8-bit registers, that is timer 0 low or timer 0 high. Although the timer 0 is a 16-bit register, but we cannot move the 16-bit number to the timer 0. We can only move the value to the timer 0 as byte-wise. That is to move the lower byte to the timer 0 low and to move the higher byte of timer 0 to the timer 0 high. The value of the timer 0 and timer 1 can go from 000H to maximum FFFFH, which is equals to 0 to 65535 in decimal. Timer 0 can receive the pulses from two sources, that is oscillator divided by 12, and from the port 3.4, that is timer 0 port, and we can program the selection, that is oscillator divided by 12 and port 3.4 from the software. If the timer 0 will receive the pulses from oscillator divided by 12, then we'll call this mode as timer mode. But if the timer 0 will receive the pulses from port 3.4 or timer 0 input, then we'll call this mode as counter mode. We can load the value of the timer 0 from 0 to 65535 as it is a 16-bit register, and we can load the value to the timer 0 in two steps, that is to move the value to timer 0 low and to timer 0 high. And if you'll use the register, that is timer 0 in timer mode, then the clock pulses will come from the oscillator divided by 12. As we are using a crystal oscillator of 12 MHz, in this case the timer 0 will be incremented by 1 MHz. If we load the timer 0 with the value that is 0, and if the timer 0 will be allowed to increment with the frequency of 1 MHz, then it will take 65535 microseconds to reach to its maximum value. It means that if the timer 0 will be loaded with a value that is 000H and will increment with a frequency of 1 MHz, it means that after every 1 microsecond the value of the counter will be incremented by 1. So it will take 65535 microseconds to reach to its maximum value. It means that 65.535 milliseconds. But if you move the value, that is 65535 minus 55535 equals to 10,000, and will allow the timer 0 to increment with a step of 1 microsecond, then the timer 0 will take 10 milliseconds to reach to its maximum value, that is from 55535 to 65535. It means 10,000 microseconds or 10 milliseconds. So we'll use this value, that is 55535, to make a delay of 10 milliseconds for our program, and we'll multiply this value by the number, that is 100, to get the delay of 1 second. And if the timer 0 will reach to its maximum value, that is FFFFH or 65535, then the value of the timer 0 will again go back to the 000H. And here we have another bit, that is timer 0 overflow flag, and this flag will be 1 if the timer will go from 65535 to the 0 value. And if we will enable the timer 0 interrupt, then this flag, that is timer 0 overflow flag, will force the program counter to jump to the value, that is 000BH, which is the interrupt vector for timer 0 interrupt. And here we can understand the concept of overflow bit. Say for example, if we have a 4-bit counter, it means that the value of the counter can go from 0 to 15, that is 16 different combinations. And here we can check for the 2 bits, that is A and B. the value is 0, 0, the value is 0, 1, 2 and 3, and after the value that is 3, both the bits that is A and B will go to the 0, 0, and the third bit that is C will be 1. So in this case the third bit that is C will serve as overflow bit, and here we can find for 3 bits that is A, B and C, here we can find all 3 bits are 1, and all these 3 bits that is A, B, C will go from 1, 1, 1 to 0. Then the fourth bit that is D will serve as overflow bit, and here we can find when all the bits that is A, B, C and D will go from 1, 1, 1 to 0, 0, 0. Then the fifth bit of the counter will serve as overflow bit, and here we can find we have timer 0, that is timer low 0, timer high 0, and the timer 0 has its 17th bit as overflow flag, and here we can find two special function registers, that is T mode and T con. The register T mode controls two timers, that is timer 1 and timer 2, and here we can find two bits, that is M0 and M1, that is to control the mode of the timer. If both the bits that is M0 and M1 will be 0, then the timer will be 13-bit timer. But if the value of M0 will be 1 and the value of M1 will be 0, then the timer 0 will serve as 16-bit timer. But if the status of the M0 will be 0 and the status of M1 will be 1, then the timer will serve as 8-bit auto reload mode. But if the value of both the bits, that is M0 and M1 will be 1, then the timer 0 will behave as split timer mode. And here we can find the same bits for the timer 1, that is M0 and M1. And here we can find another bit of T mode, that is counter oblique timer mode. If the status of this bit will be 1, then the timer 0 will be configured as counter mode, and if the status of this bit will be 0, then the timer 0 will be configured as timer mode. And here we can find the relation of this bit with an internal switch. If the status of the counter oblique timer bit will be 0, then the switch will be selected for crystal oscillator divided by 12, and the pulses from crystal divided by 12 will be applied to the timer. And here we have another selection. If the status of the counter oblique timer bit will be 1, then the pulses from port 3.4 will be applied to the timer 0. In this case, the timer 0 will be configured as counter mode. And here we can find another internal switch, that is to run the timer or stop the timer, which depends on TR0 bit, and this TR0 bit belongs to T-con register. If the status of the TR bit from the T-con will be 1, provided that the status of the bit, that is gate, will be 0, and here we can find the gate bit, the fourth bit of the T-mode register. If this bit will be 0, then the value of this internal logic will be 1, and if the status of the TR bit will be 1, then the output of this logic will be 1, and this internal switch will be closed and the pulses will be applied to the timer 0. So we have to configure these two registers, that is T mode and T con, to run the timer 0 as timer or counter mode. And here we can find another block diagram to enable the interrupt of timer 0, and here to enable the interrupts of timer 0 and other interrupts, we will use another special function register, that is interrupt enable register. And here we can find a bit which is called global bit. The status of this bit must be set to 1 to enable any interrupt in MCS 51 family. And here we can find other interrupt enable bits, that is external 0 interrupt enable bit, timer 0 interrupt enable bit, external 1 enable interrupt bit, timer 1 enable interrupt bit, serial interrupt enable bit, and timer 2 interrupt enable bit. And here in this case, if you would like to work with timer 0 interrupt, then we will set the bits, that is T0 and global bit. And if we will set these bits, and when the 17th bit of the timer will be 1, then the internal gating logic will force the program counter to jump to the address, that is 000BH. And here we can find the interrupt vectors and addresses for MCS 51 family, that is 000H for reset, 0003 for external 0, 000B for timer 0, 0013H for external 1, 001BH for timer 1, and 0023H for serial interrupt. And in our today's program, we will use a timer 0 interrupt. So we will use the interrupt vector address, that is 000BH. And here we can find our previously written program, that is counter project. And here we have constant assignments, variable assignments, ports assignments, bits assignments. Then we have directives. And here we are using two addresses, that is originate 00H. And we have written an instruction, that is jump to initialization routine on 00H. Then we have started our initialization routine from 30H location, and here we have written, that is org 30H, and here we have initialization routine. Then we have 20 millisecond delay routine to initialize the LCD, and here we have LCD initialization routine. And here in main routines we are calling three subroutines, that is go position, call print message, and print counter. And now we will modify this program to increment the counter with a delay of 1 second using timer 0 interrupt. So first we will save this file with the new name. We will go to the file, save as, and here we'll assign the name to our project, that is LCD counter project 2, and here we have assigned the name to our ASM file, that is LCD counter project 2. Okay, save. And now we'll close this project, and now we'll open new project, and here we'll assign the name, that is LCD counter project 2. Okay, save. And now we'll select the microcontroller. Okay. Right click, option for target 1. We will select the crystal oscillator frequency, that is 12 MHz in our case, and we'll go to the output and we'll check this box, that is create hex file. Okay. Now we'll add the existing file, and here we have LCD counter project 2. And now we will modify our program to increment the counter with a delay of 1 second using timer 0 interrupt. As we know that the interrupt vector for timer 0 is 0BH, so here we will write that is ORG 000BH, and here we will write that is LJMP T0ISR is the name of the timer 0 interrupt service routine, and here we have used another instruction, that is LJMP. So let's see what is the difference between jump, absolute jump, SJMP and LJMP, and here we can find the difference between different jump instructions, that is SJMP, AJMP or jump, and LJMP. The range for the addresses for the instruction, that is SJMP, is limited to the distance between -128 to +128 byte relative to the address following the SJMP. The LJMP instruction specifies the destination address as a 16-bit constant. Since the instruction is a 3 byte long and opcode plus 2 address bytes, the destination address can be anywhere in 64 kilobyte program memory space. For the instruction that is AJMP, the destination therefore must be within the same 2 kilobyte block as the instruction following the AJMP instruction. So here we have written an instruction that is originate 000BH and LJMP to timer 0 interrupt service routine. And now we'll load the value to the timer 0 low and timer 0 high to make a delay of 10 milliseconds. We will load the timer 0 value with a number which is less than 10,000 with the value, that is 65535. So first we'll minus 10,000 from 65535 number, that is 65535 minus 10,000, because 10,000 microseconds equals to 10 milliseconds. And here we have the number, that is 55,535, and now we'll convert this decimal value, that is 55,535, to equivalent hex value to load the timer 0 low and timer 0 high with the hex value. So we'll copy this number from here, and here we'll go to the selection, and here we'll select the mode of the calculator as programmer, and here we'll select the decimal value, and we'll paste the number here, Control V, and here we can find the equivalent hex value for the number, that is D8EF. So we'll use this number to initialize the timer low 0 and timer high 0, and here we can find the value EF will go to the timer low 0 and the value, that is D8, will be loaded to the timer high 0. So we'll move the value EF to the timer low 0 and we'll move the value, that is D8, to timer high 0, and here in initialization routine we will initialize the timer 0. So here we will write that is move, that is T low 0, comma hash 0EFH, and here we will write that is move TH0, comma hash 0D8H, and now we'll configure the bits for timer mode register, and here we can find from this block diagram, we will set the status of M0 bit as 1 and we'll set the status of M1 bit as 0, and the status of the remaining 6 bits will be 0 because we want to run the timer as timer mode, and we'll set the status of the gate bit as 0, then we will have 1 at the output of this OR gate, and if we'll set the status of TR bit as 1, the timer, that is T0, will start incrementing with a frequency of 1 MHz, which will come from crystal divided by 12, and after 10,000 microseconds the timer 0 will be overflow and its 17th bit will be 1, and if we'll set the bit, that is global interrupt, as 1 and timer 0 interrupt as 1, when the 17th bit will be 1, the program counter will jump to the 0B address, and now here we will initialize the value of T mode register. So here we will write that is move T mode comma hash 01H, and here we will assign a comment that is timer 0 in 16-bit timer mode, and here we will also assign a comment that is timer 0 overflow after 10 milliseconds, and now we will initialize the interrupt enable register. So here we will write that is move IE comma hash 82H, and here we will also assign a comment that is 10000010, and here we can see we have assigned the value that is 82H. That is the status of the global interrupt as 1, which makes the higher enable as 8, and here we have set the status of the timer 0 enable bit as 1. So the value of this binary number is equals to 82H, and now we clear the status of the timer 0 overflow flag bit. So here we will write that is clear TF0, clear timer 0 overflow flag, and now we'll set the status of TR0 bit as 1 to enable the timer 0 to start counting the pulses coming from the selected source. So here we will write that is set bit TR0. So we'll write that is set bit TR0. So here we have initialized the value of timer low 0 and timer high 0 for the value that is minus 10,000 from 65535. It means that after 10,000 microseconds, that is 10 milliseconds, the overflow flag bit that is TF0 will be 1, and the program will jump to the address that is 000BH, and now we will write the subroutine that is timer 0 interrupt service routine, and here after display text routine we will write the interrupt service routine that is timer 0 interrupt service routine, and here we will write that is T0 ISR, as we have assigned the name to this subroutine, and here we will write that as clear TR0 to stop the timer, and on next line we will clear the status of the timer 0 overflow flag bit. So here we will write that is clear TF0, and now we will initialize the value of the timer 0. So here we will write that is move TL0 comma hash 0EFH, and we will write that is move TH0 comma hash 0D8H, and here we have initialized the timer 0 in our initialization routine that is 0EFH and 0D8H, and now to check that after how much time the interrupt will come, we'll complement the bit that is port 1.0 of the microcontroller. So here we will write that is complement that is CPL, and here we have used a new instruction that is CPL means complement, and here we will write that is port 1.0, and now we will set the status of the TR bit as 1 to run the timer once again. So here we will write that is set bit TR0, and after executing this instruction that is set bit TR0, our program will get return from the subroutine. So here we will write that is return interrupt. It means return from an interrupt service routine, and now we'll compile our program and we will observe the result of our program on Proteus. And here we can find 0 error 0 warnings. Now to observe the time of the interrupt, we will connect an oscilloscope on port 1.0, and here we will assign the label, place a wire label that is DLY underscore 10MS is the label for port 1.0, and here we'll assign the label to the oscilloscope channel A. Place the wire label. We can select the label from the list, and now we will load the new hex file to the microcontroller. And here we have our new file that is LCD counter project 2. Okay, and now we'll run the simulation, and here we can find the status of the port 1.0 if we'll count the time, and here we can check we have set the sweep of the oscilloscope at 2 milliseconds, and here we can see we have 5 columns, that is 1, 2, 3, 4 and 5, And if we'll multiply the number, that is 2 milliseconds, by 5, we'll get the time, that is 10 milliseconds. That is 2, 4, 6, 8 and 10 milliseconds. It means that we have successfully generated an interrupt of 10 milliseconds. And now we'll write the program to increment the counter value by the delay of 1 second. And here in variable assignments, we'll define another register, that is 1 second delay register. So here we will write that is DLY underscore REG underscore 1 SEC EQU 39H. We will increment this delay register, that is delay register 1 second in timer 0 interrupt service routine to make a delay of 1 second. First we will initialize this delay register in initialization routine. So we'll copy this variable from here, Control C, and here we will write that is move the delay register, comma hash 00H, and now we will increment this register in timer 0 interrupt service routine for 100 times. And here in timer 0 interrupt service routine, we will write that is move the delay register to accumulator, that is A, comma Control V, move the value of delay register 1 second to accumulator. And now we'll compare the value of this register with 100. So here we will write that is compare jump not equal accumulator, comma hash 100, then jump to increment DLY REG is the name of the subroutine in which we will increment the value of the delay register 1 second. But if the value of the delay register will be equals to 100, then our program will come to the next line. And here we will reinitialize the value of delay register 1 second to the 00H. So we will write that is move DLY underscore REG underscore 1 second comma hash 00H, and now we will increment the value of the unit digit register. So here we will write that is move accumulator, comma UNI underscore DIG is the unit digit. And now we will compare the value, that is compare jump not equal accumulator, comma hash 9, comma INC UNI underscore DIG is the name of the subroutine in which we will increment the value of the unit digit. And if the value of the unit digit will be equals to 9, then our program will come to the next line, and here we will initialize the value of the unit digit. So here we will write that is move UNI DIG, comma hash 00H, and now we will increment the value of the 10 place digit. So here we will write that is move accumulator, comma 10 digit, and we will write that is compare jump not equal accumulator, comma hash 9, comma INC 10 DIG. But if the value of the 10 place digit will be 9, then our program will come to the next line and we will reinitialize the value of the 10 place digit. So here we will write that is move 10 DIG, that is 10 digit, comma hash 00H, and now we'll increment the value of 100 place digit. So here we will write that is move accumulator, comma HUN DIG, and we'll compare the value of the 100 digit with 9. So we'll write that is compare jump not equal accumulator, comma hash 9, comma INC underscore HUN underscore DIG, and if the value of the 100 place digit will be equals to 9, then our program will come to the next line and we will reinitialize the value of the 100 place digit. So here we will write that is move HUN underscore DIG, comma hash 00H, And now we'll write the subroutine, that is increment delay register. So here we will write that is inc underscore dly underscore reg using colon, and here we will write that is increment delay register 1 second, Control C and Control V, and after incrementing the value of the delay register 1 second, our program will come to the next line, and here we will write that is jump T0 underscore ISR underscore EXT, and now we'll write the subroutine, that is increment unit digit. So here we will write that is INC underscore UNI underscore DIG using colon, and here we will write that is increment UNIDIG, Control C and Control V, and on next line we will write that is jump T0 ISR EXT, and now we will write that is INC underscore 10 underscore DIG using colon, and here we will write that is increment 10 underscore DIG, and after incrementing the 10 place digit, our program will come to the next line, and here we will write that is jump T0 ISR exit, and now we'll write the increment routine for 100 digit, and here we will write that is INC underscore HUN underscore DIG using colon, and here we will write that is increment HUN underscore DIG, and here after incrementing the value of 100 place digit, we'll assign the label that is timer 0 ISR exit. So here we will write that is T0 underscore ISR underscore EXT using colon. Here we have completed our timer 0 interrupt service routine, and now we'll check what we have written in our timer 0 interrupt service routine. Whenever the interrupt will occur after 10 milliseconds, our program will jump to the address that is 000BH and will jump to the interrupt service routine. And here we have cleared the status of TR0 to stop the timer, and here we have cleared the status of the timer 0 overflow flag bit, and we have reinitialized the value of the timer 0 to make the delay of 10 milliseconds once again. And here we have checked the value of the delay register 1 second, and here we have moved the value of delay register 1 second to the accumulator to compare its value with the number that is 100. If the value of the delay register, that is delay register 1 second, will not be equals to the 100, then our program will jump to the subroutine, that is increment delay register, and will come here. It will increment the delay register 1 second and will jump to the T0 IR exit, and here it will complement the port 1.0 and set bit TR0 to start the timer 0 once again, and will get return interrupt from the service routine. But if the value of the delay register 1 second will be equals to 100, then our program will come to the next line, and here we have reinitialized the value of delay register 1 second to 00H, and now here we have moved the value of unit digit to the accumulator, and we are comparing the value of the accumulator with 9. If the value of the accumulator will not be equals to 9, then our program will jump to the increment unit digit, and here it will come to the increment unit digit subroutine, and here program will increment the unit digit by 1. After incrementing the value of unit digit, our program will jump to the timer 0 interrupt service routine exit. But if the value of the unit digit will be equals to 9, then our program will come to the next line, and here we have reinitialized the value of unit digit to 0, and here we have moved the value of 10 digit to accumulator, and here we are comparing the value of accumulator with 9. If the value of the accumulator will not be equals to 9, then our program will jump to the increment 10 digit, and here in increment 10 digit, it will increment the value of 10 place digit and will jump to the timer 0 interrupt service routine exit. But if the value of the 10 place digit will be equals to 9, then we have reinitialized the value of 10 place digit to the 00H, and we have moved the value of 100 place digit to the accumulator, and here we have compared the value of the accumulator with 9. If the value of the accumulator will not be equals to 9, then our program will jump to the increment 100 digit routine, and here our program will increment the 100 place digit, and after incrementing this digit, it will complement the status of the port 1.0 and set bit TR0 and will get returned from the subroutine. But if the value of the 100 place digit will be equals to 9, then our program will come to the next line, and here we have reinitialized the value of 100 place digit to the 00H, and now here we will write another instruction, that is jump T0 ISR exit So here we have completed our timer 0 interrupt service routine. Now we'll compile the program and we'll observe the result of program on Proteus. And here we can find 0 error, 0 warnings. And now we will run the simulation. Here we can find the counter is incrementing by a delay of 1 second. The maximum value of the counter will be 999, and after counting 999, the counter will go back to the 000. In this session, we have learned that how to increment the counter with a delay of 1 second using timer 0 interrupt. In our next session, we will incorporate 3 switches, that is switch 1, switch 2 and switch 3. Switch 1 to start the counter, switch 2 to stop the counter, and switch 3 to reset the counter. So in next session, we will learn that how to incorporate these switches in our program. Thanks for watching this semi-language programming course. We hope that you find this course very helpful to learn semi-language programming. If you feel that this course contributes and enhances your embedded system design knowledge, then go ahead and hit like, share and subscribe buttons, and do not forget to press bell icon to stay updated with every new upcoming video from Electro Educators as soon as it goes up. Electro Educators also offers technical consultancy in following fields. For assistance regarding technical problems, projects and any consultancy, feel free to reach out at our email address electroeducators@gmail.com. Okay, see you in next lecture.